In this video, we'll talk about deep learning and neural networks. Have you ever wondered how Google can translate an entire web page in no time from almost any language to another? Or how Google Photos magically sorts your pictures based on the faces of people and pets it recognizes? Or how about when Google Lens fills you in on the details of a plant, object, or animal when you scan it with your phone? That's deep learning working its magic right there. In this video, let's try to answer the question of what is deep learning and how it makes all these incredible things possible. In this video, we'll be discussing the following topics. We'll start with an understanding of deep learning and then move on to artificial neural networks, which are a type of machine learning algorithm that are used in deep learning. We will then explore some of the practical uses of deep learning and introduce some of the most popular deep learning platforms. And finally, we'll discuss some of the limitations of deep learning and how quantum computers can tackle those limitations. It's going to be an exciting session on deep learning. So, as we said earlier, deep learning is a subset of machine learning, and both are parts of the bigger concept called artificial intelligence. Imagine artificial intelligence as the whole realm of making machines act like humans. Machine learning is a part of that realm, and it's all about giving machines the ability to learn and make decisions based on data, kind of like how we learn from experience. Now, deep learning is a more specific part of machine learning. It's like teaching a machine to think a bit like a human brain with a structure called an artificial neural network. Artificial neural networks, or ANNs, are a specific type of machine learning algorithm that try to loosely mimic the neural networks in the human brain. When we say deep learning, we're usually talking about using really big neural networks to train a model on loads of data. It's not different from machine learning, just a fancier term we use when things get pretty big scale. So, what are artificial neural networks? Let's have a closer look at the construction of a neural network. Each layer consists of nodes, or what we call neurons. The neurons in one layer connect with neurons in the next layer through channels. Each channel is assigned a weight, which plays a significant role in the network's learning. Every neuron has an associated bias and an activation function. The activation function is used to transform the weighted sum of the inputs and the bias into an output that is sent to the next layer. As we said before, ANNs sit at the core of deep learning. These algorithms are crafted in a way that mirrors the working of the human brain. They absorb data, learn to identify patterns in the data, and then make educated predictions for a new set of data. Let's explore the process by building a neural network capable of distinguishing between a cube and a pyramid. Consider an image of a cube as an example. This image is comprised of 28 by 28 pixels, resulting in a total of 784 pixels. Each pixel is then provided as input to individual neurons within the first layer. Neurons in one layer are connected to neurons in subsequent layers through channels. The inputs are multiplied by their corresponding weights, and then the bias will be added to it. This combined value then undergoes evaluation through a threshold function, known as the activation function. The result is transmitted as input to the neuron within the hidden layer. Then, the output of the activation function determines whether a neuron becomes activated or not. Activated neurons transmit data to the neurons in the next layer via the channel. This iterative process, known as forward propagation, enables the data to propagate through the network. Within the output layer, the neuron with the highest value becomes activated and determines the final output. These values are essentially probabilities. In this particular scenario, the neuron associated with the pyramid has the highest probability, indicating that the neural network predicts the output as a pyramid. Well, obviously, our neural network has made an incorrect prediction. It's important to note that at this stage, our network has not undergone training yet. So let's have a look at the steps for training a neural network. During the training process, the network receives both the input and the expected output. By comparing the predicted output to the actual output, the network identifies the error in its prediction. The magnitude of the error indicates how wrong we are, and the sign suggests if our predicted values are higher or lower than expected. This information is then propagated backward through the network, a technique referred to as backpropagation. Through backpropagation, the network adjusts its internal parameters, such as the weights and biases, to minimize the error and improve its future predictions. The iterative cycle of forward propagation and backpropagation is repeated with multiple inputs during the training process. This cycle continues until the weights within the network are adjusted in a way that allows the network to accurately predict the shapes in the majority of cases. This marks the completion of our training process, where the network has learned to make correct predictions. Although training neural networks can be a time consuming process, sometimes taking hours or even months, the investment of time is justified given the immense possibilities they offer. The intricate nature of training involves fine tuning numerous parameters and optimizing the network's performance, requiring significant computational resources and patience. However, the benefits gained from a well trained neural network, such as improved accuracy, advanced pattern recognition, and sophisticated decision making, outweighs the time spent in training. It's a reasonable trade off considering the remarkable potential and capabilities the neural networks bring to the table. Now, let's have a look at some of the applications of deep learning. As we said earlier, it is the power of neural networks that makes deep learning possible. Let's explore some of the key applications where neural networks shine. One notable example is facial recognition technology on smartphones, which utilizes neural networks to estimate a person's age based on their facial features. By distinguishing the face from the background and analyzing lines and spots, these networks correlate the visual cues to approximate the person's age. Neural networks also play a crucial role in forecasting, enabling accurate predictions in various domains such as weather forecasting or stock price analysis. These networks perform very well in recognizing patterns, making them able to identify signals that indicate the likelihood of rainfall or fluctuations in stock prices. Neural networks can even compose original music. They can learn intricate patterns in music and refine their understanding to compose original melodies, showcasing their creative potential. And another area where neural networks excel is customer support. Many individuals engage in conversations with customer support agents without even realizing they are actually interacting with a bot. These sophisticated networks simulate realistic dialogue and provide assistance, enhancing customer service experience. Also, in the field of medical care, neural networks have made significant strides. They have the ability to detect cancer cells and analyze MRI images, providing detailed and accurate results that aid in diagnosis and treatment decisions. And obviously, we also have self driving cars. Once only a possibility in science fiction, now they become a tangible reality. These autonomous vehicles rely on neural networks to perceive and interpret the environment, enabling them to navigate roads, make decisions, and ensure passenger safety. And with that, let's have a look at some popular deep learning frameworks. So, some of these frameworks are TensorFlow, PyTorch, Cross, Deep Learning 4J, Cafe, and Microsoft Cognitive Toolkit. These frameworks have gained widespread recognition and play a significant role in advancing the field of deep learning. And now let's discuss some of the limitations of deep learning. While deep learning holds tremendous promise, it is important to acknowledge its limitations as well. So, firstly, although deep learning is highly effective in handling unstructured data, but it needs a substantial amount of data for training purposes. The second problem is that even assuming that we have access to the required data, processing it can be challenging due to computational power. Training neural networks demands the use of graphical processing units or GPUs, which have thousands of cores compared to central processing units or CPUs. And at the same time, GPUs are way more expensive than CPUs. And finally, training is time consuming. Deep neural networks can require hours or even months to train, with the duration increasing as the volume of data and the number of network layers increase. That said, it is worth mentioning that quantum computers developed by companies such as Google and IBM offer a potential solution to overcome these limitations. Quantum computers have the ability to perform complex computations at an exponentially faster rate than classical computers. With their unique architecture and quantum processing units or QPUs, they have the potential to significantly accelerate the training process of neural networks. In addition, quantum computers can handle large scale datasets more effectively, reducing the data requirements and mitigating the challenges associated with processing such vast amounts of information. While quantum computing is still in its early stages, the ongoing research and development hold the promise of overcoming the limitations faced by traditional deep learning approaches. Thank you for exploring the world of deep learning with me. It is crucial to acknowledge that we are still in the earliest stages of exploring what deep learning and neural networks can do for us. However, big names like Google, IBM, and NVIDIA have recognized this growth trajectory, investing in the development of libraries, predictive models, and powerful GPUs to support the implementation of neural networks. We are almost at the end of this section on traditional artificial intelligence. It's important to note that we have merely scratched the surface when it comes to the potential of deep learning and AI. Exciting possibilities lie ahead. As we push the boundaries of what is possible, the line between science fiction and reality becomes increasingly blurred. The future holds an overload of surprises, and deep learning is at the forefront of these groundbreaking advancements. In the next video, which is the last video of this section, we will learn the difference between discriminative and generative machine learning models, which will prepare us for the next section of this course on generative artificial intelligence. See you in the next one.